Okay, 2024 OCR B H557 paper 2, that's the one you're doing. There's an advanced notice article called Seeing Beyond the Stars, Seeing Beyond the Visible, beg your pardon. Hopefully you've got your copy now, your teacher's given you a copy. If you want a spare copy, you can download it off the OCR website. So I've got mine and I've had a bit of a read of it and some thoughts on what I think of it, some of the questions that might come up. Okay, if you have any ideas, please add them to the comments. I'm sure other viewers will be grateful for your ideas as well. So you've got this figure 1, which is showing the different parts of the electromagnetic spectrum, what wavelengths can pass through the Earth's atmosphere easily, and we're told in the article it's visible and radio, and apart from one little kind of around 10 to the 7 microwaves as well, which is why all your communications satellites and all use microwaves. One of the reasons they use microwaves. What types of wave are absorbed the most, and it looks as though it's ultraviolet and X-rays, and gamma struggles to get through, infrared struggles to get through. Look at the graph yourself. Obviously you should have this article, you know, and you should know what I'm talking about. The half absorption altitude, I reckon that's the altitude at which half of it is absorbed. So for example, for the wavelength 0.1 10 to the minus 1 nanometers, at 60 kilometers, half of it is absorbed, the half absorption altitude. Why are Earth-based telescopes often sighted at high altitudes? Well, because basically, you know, apart from visible and radio, the higher up you are, the less of this radiation will have been absorbed. So the more intense it will be, the stronger the signal you will get. For example, one of the highest ones, there's some telescopes, gamma and infrared telescopes in the Himalayas at about 4.5 kilometers up. Now, if the atmosphere was uniform density, and it isn't, but if the atmosphere was uniform density, then for any particular wavelength, the amount of radiation that gets through would fall exponentially. It's one of the things that you should know is like gamma radiation with distance follows an inverse square law. Gamma radiation with the thickness of the absorber is an exponential relationship. And the intensity of radiation getting through the atmosphere would also fall exponentially. Maybe there'll be some kind of question on that. Now, that is if the atmosphere was uniform density, but it isn't. The density of the atmosphere, atmospheric pressure, actually decreases exponentially with altitude. So as a result of that, most of this radiation is absorbed closer to the Earth, where the atmosphere is denser, yes, where atmospheric pressure is greater. There may be something like this, I don't know. It's a mathematically kind of thing. Resolution. Now, resolving power. What do we mean by resolving power? It's the ability of an optical instrument, for example, your eye, to tell 2 points apart. Okay, if you see 2 points, imagine I did 2 dots. Let's get the pen out. If I did 2 dots on a bit of paper like that, yes, and then you walk further and further and further and further away from it, at what point will you only see 1 dot? In other words, at what angle? It's a limit, the limit of your resolution, theta lim, it's your angular resolution, is the smallest angle at which you can tell those 2 points apart. You can resolve between them. Resolution is one of these words on our syllabus. You know, you talk about the resolution of a digital image, and that has a different meaning. Okay, similar meaning, but different. Basically, it's the smallest angle that you can tell 2 points apart. And it depends on 2 things. It depends on the wavelength of the radiation, and it depends on the diameter of the aperture. The aperture is the hole that the radiation comes through. If it's your eye, then it's the diameter of your pupil. If it's a telescope, it's the diameter of usually of the objective lens, the big lens at the front. Okay, so it depends on the wavelength and it depends on the diameter of the aperture. So radio telescopes need very, very big distances. Basically, theta lim, if theta lim is small, then that's good. Now, for theta lim to be small, you want big D and you want small lambda. Now, radio is big lambda, so that's going to mean theta lim is rubbish, it's too big. So you need D to be big as possible, okay? Some of these radio telescopes, and you can actually combine them together, so you end up with these effectively massive telescopes. Calculate the resolving power of the Jodrell Bank telescope. I'd bet 20 pence you'll be asked to do that. You're given lambda, you're given the diameter. Estimate that of the unaided eye. So you need to estimate kind of visible light is about 600 nanometers. I always say that's kind of average for visible light, 600 nanometers. Your pupil at night time has a diameter of about a centimeter, maybe a little bit less than that. So you can estimate that of the unaided eye. Now, resolving power, it may come up about where this equation actually comes from. When light goes through a circular aperture, you get a diffraction pattern. Now look at these diffraction patterns here, which is like a bright spot and then kind of a minimum and then a maximum after that. So it's like rings. It's actually called an airy disk. It's on other syllabuses. It's on in GCSE astronomy as well. Now, if you look at 2-point light sources, what happens when they get closer and closer together is that the two patterns start to merge together, and eventually there isn't a dark bit in the middle. And when there isn't a dark bit in the middle, that's when you can't tell them apart. Okay, so it's to do with when the single slit or single circular aperture diffraction patterns merge together. There might be something to do with that. Here's an interesting photo on the right here, which is the first one is a ground-based telescope, and the second one is a Hubble telescope looking at the same thing. And clearly with the Hubble one, you can see that there are two stars. With the ground-based one, it just looks like one star to me. Telescopes in space. Why put telescopes in space? Because you're above the atmosphere. So you can observe all these different wavelengths that can't get through the atmosphere. Why put it in an elliptical orbit? This is the Chandra X-ray Observatory. And this is basically because surrounding the Earth, there's all kinds of rings of ion charged particles whizzing around. This is called the Van Allen belt. And if you like, on this diagram here, it's loads and loads of charged rubbish particles which are going to interfere with your signals. So apparently it's something like in 85% of the orbit of this telescope, you're outside of the effect of these charged particles. Okay, so that's why they put it in an elliptical orbit. I imagine here now, apogee is the furthest away it is, which is A on the diagram. Perigee is when it's closest. I got these values of R actually off the internet, and there is an equation to work out. Now, it's not a circular orbit, so in this particular case, it is not V equals root gm over r, yeah, which would be a circular orbit. It's actually an elliptical orbit, and the equation's a bit trickier than that. But nevertheless, they're the maximum and the minimum velocities there. You can work out the potential minus gm over r for those two particular radii. You can work out the kinetic energy, you can work out the GPE, Notice that the GPE and the potential are both negative. The total energy should be the same, I suppose, I mean, you know, about 10 times 10 to the 10, 10 times 10 to the 10, I'm being a bit generous there. Is it rounding errors or some of my numbers are wrong? I don't know. But some kind of question involving kinetic energy, gravitational potential energy, the total should stay the same. So here, the satellite is traveling slow. Here, the satellite is traveling quick, okay, because kinetic energy and GPE, etc., you know what I'm on about. The L2 point, Lagrange 2 point, is over here. Why? Because relative to the Earth, you're always as far away from the sun as you can be for this particular orbit. You know, you don't get kind of closer to the sun as it goes around the Earth or whatever. So you're always far away from the Earth, the same distance from the Earth, okay? The L2 point, okay? And what happens is that as the Earth goes round the sun, then the satellite will also go round the sun with the Earth. So omega will be the same. So this satellite will have a period of 365 days. Yeah, it'll have the same angular velocity as the Earth. Now, if R is bigger, then does that mean that you would need a bigger force acting on the satellite? Well, the gravitational pull of the sun on its own is going to be weaker because it's further away. But you've also got the gravitational pull of the Earth. So what I'm saying is that you've got the acting on the satellite, you've got the gravitational pull of the sun, and you've got the gravitational pull of the Earth. So yes, R is bigger than Earth, but F is also bigger because it's these two centripetal forces combined so that you can have the same omega. If R is bigger, then F would need to be bigger for omega to be the same. At the bigger value of R, the gravitational pull of the sun is smaller. However, the extra force is provided by the gravitational pull of the Earth. That's what I just said. Now, it's actually going in two circles. So it's going in the big circle around the Earth, but it's actually also going around in a circle like this. Okay? So you would need a centripetal force for the big orbit, and you would need a centripetal force for the small circular orbit, and there's nothing at the L2 point. So I reckon that the resultant force acting on the satellite, you could split that into two components. And one of the components is the centripetal force for the big orbit, and then the other component will be the centripetal force for the small orbit. Yes, revise circular motion. Yeah, there'll be questions on circular motion. JWST is an infrared telescope. Okay, so 600 nanometers, which is actually visible, to 29 micrometers. Okay, an infrared telescope. You'll see on that graph at the beginning, that's the range of wavelengths there. Why should its instruments be kept as cool as possible? Well, basically we want to detect heat radiation, and to detect heat radiation the instruments need to be cold, so that the only infrared involved is the stuff that we want to detect. This is one of the ways that it's always shielded from the sun by the Earth. It always faces away from the sun and Earth, but if you like, I imagine there would always be like a solar eclipse. Instead of the moon getting in front of the Earth, it would be the Earth, sorry, instead of the moon getting in front of the sun, it would be the Earth getting in front of the sun. So there'd always be like an eclipse if you lived on the JWST. So the Earth helps to shield it. It's always facing away from the sun and Earth. It's got all these sun shields. If you look at other pictures of JWST, these massive kind of big as a quarter of a football pitch or something shields, and it has a cooling system as well. NIR cam, near infrared, near because it's near to visible. Yes, in terms of wavelength, yeah, it's near to the visible. So the NIR cam, and you're given some dimensions of it and how many pixels, that many pixels by that many pixels. You're told the field of view, and the field of view in milliradians. Yes, what angle it covers in the sky, the field of view. So you can work out the angular resolution, yes, in radians per pixel. It's actually, I looked it up, 16 bits per pixel. So there might be a question on maybe image size or something like that. You have some kind of a spectrometer, which is going to split the radiation up into different wavelengths so that you can measure the intensity of different wavelengths. So there may be some kind of a diffraction grating question. N lambda is d sine theta, because your spectrometer would involve some kind of clever diffraction grating thing. In terms of visible light and looking at the range of wavelengths, it will pick up red. It'll basically pick up red and lots of infrared. It won't pick up any wavelengths smaller than red. This is your hydrogen energy levels. Your Balmer series is your visible. This series here, the Lyman series, that's ultraviolet. This is your Passion series, that's infrared. So basically working out kind of using this diagram, 600 nanometers is about 2.07 electron volts. To 2300 nanometers is about 0.54 electron volts. Which of these transmissions would be detectable? Well, it's the 2.07 electron volts. If you look at this one here, yeah, that's just less than that. So that would be your, what we call the hydrogen alpha. Yes, so that would be visible, and all of these infrareds would be visible as well. Yeah, they'd be within that range of photon energies. Okay, so I mentioned the angular resolution, so you can work out horizontally the angular resolution and vertically the angular resolution. Interestingly, going back to the diagram with the squares on, there's actually little gaps between them, and some of the pixels around the edges are actually used to detect other things. So it's not like one big uniform rectangle, and maybe that's why the two angular resolutions are a little bit different. So this was a JWST image of Saturn, and that's now Saturn at its closest to Earth. Well, I don't know if that includes the James Webb Telescope as well, but imagine Saturn is that distance away. What distance between 2 points on the surface that you could resolve, that you could tell apart, and using, let's say, using the horizontal angular resolution, it works out at about 206 kilometers. Basically some kind of a calculation using the angular resolution. Hubble goes on about Hubble, waffles on about that. Basically Hubble's graph, the recession velocity is proportional to how far away it is. H0 is the Hubble constant. How does this graph show that the universe is expanding? Because it shows that all of these galaxies are moving away from each other. Yes, if the ones that are further away because they're moving faster, then back in time everything must have been closer together. It shows that the universe is expanding. This equation is mentioned. Delta lambda over lambda is V over C. The Hubble constant, it's actually now, it might give you it in kilometers per second per megaparsec, where a parsec is 3.2 light years, or it may just give you it in seconds to the -1, which I'm thinking is probably more likely. But I imagine there would be some kind of a calculation where you have to work out the recession velocity and therefore work out the distance, either just in meters or in megaparsecs. Anyway, there you go. It talks about now why infrared. Why is observing infrared so useful? Because a lot of the stuff which is emitting infrared we don't see because it is absorbed or scattered or emitted by clouds of dust, and so we can't see what's behind the clouds of dust. So absorb, scattered means like flying off in all directions, and obviously this dust and talks about little ice particles as well. So basically it allows us to see inside and behind these big clouds of dust. Okay, obviously these lovely images that we can see are false color images, and on our syllabus we should know what that means. Yes. Evidence for potential of life. What would that be? What would be the evidence for potential of life? Maybe detecting exoplanets. Goldilocks zones means it's not too close to the sun, the star, because then it would be too hot, not too far away because it would be too cold, just at the right distance, so it's just right, the Goldilocks zone. If it detected water, evidence of water or oxygen or even organic compounds, maybe that would be evidence for light. Anyway, that's my thoughts on the kind of questions which might come up. As I said, if you have any ideas, then say so in the comments. Let's get a bit of a discussion going.